shifting center of motion. So far, all of the simple harmonic motion we've been looking at, right? It has a center of motion at the origin. Okay, now we've dealt with questions where it's not, but I haven't addressed it formally. So let's come back to our first idea of the displacement of some kind of particle object. If it's going to exhibit simple harmonic motion, it must be a wave function, right? So let's take this as just a general example. Okay, obviously I could have chosen cosine, but what I'm going to demonstrate is going to work exactly the same anyway. There's your amplitude, that's where your period comes from, there's your phase shift, okay? Now, let's just rehearse the result for x double dot, okay? Just do it by differentiation. So if we differentiate once to get velocity, okay, it's chain rule, so that m comes out at the front, so I'm going to get a, m, sine turns into cosine, and what's inside the trig function stays the same. Differentiate again, and you will see the familiar result, the differential equation we're familiar with, again come out because n comes out the front, another one, so that's a m squared, right? Cosine turns into negative sine, so slap that minus sign out the front. There's sine nt plus alpha. Okay, so you can see now, if I put this a over here, which is a bit of a weird spot to put it because it's not alphabetical, but you can see that it's just x, right? And there's my minus n squared. So there's my differential equation. All happy, okay? Now if I want to reposition the center of motion, move it up or down somewhere else, okay? If you come back to this displacement equation, right? You can take the same old wave function, a sine nt plus alpha, right? And to just change where it is in terms of position, all I need to do is add or subtract a constant, right? So let's call that constant x naught. What that's going to do is, in this case, I'm moving up x naught units. So if x naught is negative, I'm going down, okay? Or left. Left or right, you get the idea. All right, now, let's just keep this in mind and go through the same process, right? So when you get to x dot, okay, differentiating, because it's just a constant, it vanishes. So in fact, I'm going to get the same results that I got on the left-hand side, right? Because it's almost identical. So I'm still going to get an cos nt plus alpha, and I'm still going to get minus an squared. Okay. So you can see that I can't call this minus n squared x, right? Because n squared x would be including this constant, right? So I need to rejig it a little bit so that I get a new differential equation, okay? Now, what's the key? See that, I might actually rearrange this. Let's put the n squared out the front. And I'll put the a there. Okay, now, this, I can see I'm substituting for that, okay? I have something a little bit different here, right? So what am I going to do to enable me to sub into this equation? Well, if I rearrange this a little bit, right? Get my a sine nt plus alpha on its own, okay? So that I can sub it into here, the a sine nt plus alpha. All I have to do is kick the x naught to the other side, right? Which sort of shouldn't surprise us, because when you've got x minus something, that's how we normally do a shift of like a parabola, x squared to x minus 2 squared or something like that, okay? So therefore, this is going to be, this a sine nt plus alpha will sub in for this whole thing, okay, the whole right-hand side. So I'm going to get this. Okay? So there's a new differential equation. It still exhibits simple harmonic motion because it's still a wave function, right? But you can see the equations are just ever so slightly different. Okay? So either of these, if you show them, that's enough to prove simple harmonic motion. Let's have a look at an example.